Hello everyone. It is my great pleasure to present our recent findings related to the sophisticated dynamic disintegration of concrete structures by controlling wave motion at the 23rd European Conference on Fracture. This is Koji Uenishi at the University of Tokyo. I have been looking forward to attending the conference for a long time, but unfortunately, due to the pandemic, it is still practically difficult to visit the Madeira Island from Japan. So, I am going to deliver a video presentation. We are grateful to Professors Moreira and Reis and the organizing committee of the conference for providing an opportunity to give this video talk on controlled structural disintegration, performed with my co-workers at the Sumitomo Mitsui Construction Company. Let us briefly mention the background. The number of surface and underground structures that are reaching their normal duration of life has been remarkably increasing, and in order to efficiently dismantle such aged structures, either partially for renovation or totally for reconstruction, dynamic technique of blasting by detonating explosives may be employed. Blasting demolition may be accomplished in a very short time span, but it is still planned by experience and may become extremely complex and difficult for reinforced structures that have been constructed very tightly. Hence, blasting tends to be carried out at an overcharge level of explosives that will cause complete destruction, but at the same time, may produce excessive energy for the operation. This may result in unwanted and/or dangerous failures, which is one of the main reasons blasting demolition is usually avoided in densely populated urban areas. Therefore, in place of explosives, by using safer and more controllable electric energy, and based on the theory of wave and fracture dynamics, we have been investigating more reliable technique for precisely controlled dynamic disintegration of structures with and without reinforcements. So far, by applying electric discharge impulses, EDI, we have successfully, namely, as desired, disintegrate rectangular and cylindrical concrete specimens. We have found that specific combinations of blast holes, empty dummy holes as well as free surfaces and pre-existing planes of weakness can really govern the dynamic behavior of the waves and the main crack, and thus the disintegration pattern in given structures. Here, among others, we are going to talk about the following 4 selected examples of dynamic fracture due to EDI-induced waves. First, fundamental fracture development in a concrete column will be introduced. Then the effects of empty dummy holes, slits, and structural inhomogeneities on dynamic fracture will be briefly mentioned. Let us start with our electric fracturing system, EDIX, developed by Nitazotech or Hitachi Zosen Corporation. In EDIX, a cartridge containing self-reactive liquid is prepared, and the electric energy stored in a capacitor is discharged in the self-reactive liquid within several hundreds of microseconds through an electronic switch. Then, high pressure is generated due to the rapid evaporation of the liquid. In the following field experiments, these cartridges are placed in blast holes, covered by stemming material, and connected to the control unit of EDIX. Here is the setup of our very basic experiment. We have prepared a cylindrical specimen made of concrete without reinforcing steel bars. The specimen has one blast hole at the center along the vertical axis, with the cartridge located at the very center of the specimen. The model is symmetric with respect to the blast source or cartridge, except for the stemming section. In the field, the specimen is placed and subjected to EDI in a pit where the dynamic fracture process due to the action of EDI is recorded by a normal home video camera and by a high-speed camera at a frame rate of at least 50,000 frames per second. This slide, showing typical development of dynamic fracture taken by a normal home video camera, indicates the rather strong power of the EDI. According to the photographs, the cracks on the top surface seem to have run unidirectionally from the central blast hole to the edge, but in reality, as we see on the next slides, the cracks are formed by the combination of the outbound fracture propagating from the center and the inbound one moving from the edge to the center. Indeed, detailed observations by the high-speed camera reveal that on the top surface, a crack extending outbound from the blast hole located at the center as well as that propagating inbound from the edge to the center may be identified. The outbound and inbound cracks may extend, and may or may not merge, at a later stage. After the crack development, we see the crack openings are widened by some gas pressurization. Thus, like in conventional blasting using explosives, we may expect also in the case of EDI crushing that cracks from end to the center develop first by the direct and reflected EDI-induced blast waves, and then gas pressurization takes place. The next example shows an unusual effect of empty dummy holes on the direction of dynamic fracture propagation due to the application of EDI. This time, a rectangular concrete block without reinforcing steel bars has been prepared, and each of the 3 blast holes, indicated in red, are surrounded by a set of dummy holes that are indicated in blue. EDI is applied to each of the 3 blast holes simultaneously. We expect that due to the superposition of the reflected waves from these dummy and blast holes, a main tensile crack extending rather straight and connecting only blast holes will develop, at least near the center of the specimen. The unusual point here is that dummy holes are not placed on the expected main crack path or the fracture plane, and they are set rather to direct the main crack to connect the blast holes only. Here is the top view of the specimen during and after the simultaneous application of EDI. On the right, we notice that especially in the central part, the main crack extends rather straight as desired. Near the free surfaces and screw holes on the sides, however, we see some unwanted cracks. Further observation of the crack development in the rectangular specimen by the high-speed camera, shown on the left, indicate that the main crack running through the 3 blast holes and the cracks in the 2 squares formed by the dummy holes near the free surfaces on the sides appear almost at the same time. Again, it seems that the dynamic fracture network induced by EDI develops first upon wave propagation in the specimen, and then gas pressurization widens crack opening displacements and the stemming material is ejected, like noted in conventional blasting by explosives. The above experimental observation of the unusual role of empty dummy holes can be supported by our 3-dimensional finite difference simulator running on a PC. Numerical details are omitted here, but we assume homogeneous, isotopic, and linear elastic concrete material, and the values related to material properties and EDI-induced time-dependent pressure are inferred from the experimental observations. Although different physical quantities may be chosen, for simplicity, the stemming material covering the cartridge and filling every blast hole is presumed to have the same material properties as concrete. Also, although technically simply implemented, no specific fracture criterion is incorporated at this moment, because, first of all, we must know how waves generated by the new technique, application of EDI, propagate and interact with given inhomogeneities. Then, as seen in the animation on the right and the snapshot on the left, we can confirm numerically that tensile regions close to the free surfaces and dummy holes as well as those near the middle blast holes seem to appear almost simultaneously, possibly due to the existence of waves reflected from the nearby holes and propagated towards the middle blast hole, and a tensile crack plane connecting the 3 blast holes will emerge rather smoothly at a relatively earlier stage, as expected from the experimental results. The third example is the dynamic disintegration of sections in large concrete slabs without reinforcing steel bars. By setting in advance vertical slits inside large, unreinforced concrete slabs, we have tried to control wave interaction and dynamic structural disintegration. As seen here, the concrete slabs are split into rectangular sections with slits of depth 70 mm. Each section has 6 blast holes along the center line that are simultaneously pressurized with EDI. This photograph taken after the application of EDI shows that a main crack running through the blast holes can be generated as desired. Together with the horizontal fracture plane connecting the bottoms of the slits, only a rectangular part can be efficiently removed from concrete slabs. The relative positions of the blast holes to the top free surface and preset slits, compared with the wavelengths of EDI-induced waves, may play an important role in generating final fracture pattern. Again, our fully three-dimensional finite difference numerical code for a PC may well explain the real field observations qualitatively. The waves generated around the cartridges are initially compressive, and then tensile zones due to reflection at the top free surface and the slits emerge, which may induce cracks. Plotting only the zones of larger tension, shown on the right, clearly indicates that tensile zones which are likely to be more easily fractured can be identified only inside the rectangular section bordered by the top horizontal free surface, vertical slits, and the rather flat horizontal plane near the bottoms of the slits. The final example of the usage of EDI-induced waves for controlled dynamic fracture is related to a steel concrete composite structure that consists of a reinforced concrete slab on top of a steel girder and stud dowels or shear connectors. Here, we have 8 blast holes and 9 stud dowels inside the model. The objective is to crush and remove only concrete material by EDI-induced waves while other parts of structures like stud dowels and steel girders remain undeformed for later renovation work, even in densely populated urban areas. The experimental result shows that concrete material can indeed be removed without impact on the stud dowels and steel girder. Here, a horizontal fracture plane connecting the heads of the stud dowels and another horizontal fracture plane linking the cartridges are generated. The concrete material above the heads of the stud dowels can be lifted and removed as a rectangular block, and in other parts of the reinforced concrete slab, due to the action of EDI, the concrete is fragmented into smaller pieces, most of which can be taken away by hand or with a crowbar. Three-dimensional finite difference simulations can show that the plane virtually formed by the heads of stud dowels are expected to act as an interface that prevents the transmission of tensile waves, and thus generate the observed unique fracture. However, if the distance between the stud dowels is increased, the role as a virtual interface can be lost. Now our conclusions are listed. Thank you for your kind attention.